I'm not going to talk about this concept 2.2 in your textbook, the properties of elements and the relationship between these properties of elements and the structures of its atoms. As I said before, I assume that you have a background and you know what is an atom, what is an element, what is a molecule, what are ionic compounds. So I'm going to, in the next section, talk very briefly about that. But if you don't know these things, please go and read it in the textbook. I want that you make sure that you know what is an atom, make sure that you know what is a nucleus of an atom, know what is an orbital. I want that you remember, go and check if you know what is a protons, what are atomic number. Make sure that you know that protons and electrons have an equal number, like they show you here. So in your textbook is very well explained, but I'm not going to talk about that because I'm sure that most of you know it. I'm going to talk later about covalent and non-covalent bonds and chemical equilibrium. So now let's move to the next concept, that is the chemical bonds. And this is a terrible joke of the day. So do you remember the bonds? So when I was preparing this lecture, I found this really bad joke. We're going to study chemical bonds. Now we're going to study the distribution of electrons, and I'm going to show you that they determine the properties, the chemical properties of an atom. And I want that you remember this, that some atoms may react with each other by sharing. So here you can see one that is sharing, others will donate, and other one will receive electrons. And this will allow something that the atoms stay close together, and these attractions are called chemical bonds. And I want that you remember three main chemical bonds. The first one are called covalent bonds, and remember the covalent bonds are sharing electrons. The other ones are the ionic bonds that are transferring electrons between ions. And the third one are the weak bonds, and the most important ones are these hydrogen bonds that they are very important for life, that they are electrostatic attraction. So remember, chemical bonds allow two atoms to stay close together, and they are held by attractions. And we're going to focus on three: covalent bonds, ionic bonds, and weak bonds. There are three main subatomic particles: protons, neutrons, and electrons. But the most important of that to determine the chemical properties are the electrons that are directly involved in the chemical activity because they are involved in the chemical bonds. And electrons occur in energy levels called electron shells. In a second, I'm going to show you an example of these four elements that we talked when we say that they were very important. But first of all, before that, I want that you watch a video of the textbook that explains very well what is an electron shells.
Energy levels of an atom's electrons. This diagram shows a model of one atom with the nucleus at the center and electrons around it. Electrons move rapidly around the nucleus at discrete average distances according to how much energy they have. Here, the electron energy levels, called electron shells, are shown as flat circles around the nucleus, but the electrons are actually buzzing in 3 dimensions, so each circle represents a spherical region around the nucleus. In the figure, only a section of the model is shown. Electrons can have different amounts of energy depending on how fast they're moving and how far they are from the nucleus. In this figure, we're looking only at the energy due to their location, called potential energy. Each shell represents a different amount of potential energy that an electron can have. Electrons with the lowest potential energy spend their time in the first electron shell, closest to the nucleus. The negatively charged electrons are attracted to the positively charged nucleus, but they never fall into it because of their momentum. The farther an electron shell is from the nucleus, the higher the potential energy of the electrons in that shell. An electron in one particular electron shell needs to absorb a discrete amount of energy in order to move to a shell farther away from the nucleus. As an analogy, imagine a ball sitting on a set of stairs. The ball can rest only at discrete levels, or steps. If it's going down, it falls from step to step. And if it's being pushed up, it can only stop to rest when it reaches the level of the next step. In either direction, it can't stop in between steps. Likewise, electrons can only contain certain amounts of potential energy and exist certain distances from the nucleus. They move from electron shell to electron shell by gaining or losing the discrete amount of energy that it takes for them to reach the next shell. Keep in mind that the electrons are constantly in 3D motion, unlike the ball in this stair analogy, so the steps represented by shells are average distances from the nucleus as electrons buzz around it in all directions. Why does an electron need to absorb energy to move out to a higher shell? Because it needs energy to pull away from the attraction of the nucleus. The energy might come from a photon of light, or another energy source that delivers the exact amount of energy to boost the electron out to a higher shell. It might happen in 2 steps, as shown here, or in 1 big step, as shown here. In either case, the electron now has more potential energy, and it moves around the nucleus at a higher energy level in a shell farther from the nucleus. We often call an electron that's been boosted to a higher potential energy level an excited electron. Electrons don't stay in an excited state very long before they drop back down to lower shells, giving off energy in the process. How much potential energy will an electron lose as it drops down from shell 3 to shell 2? As excited electrons drop down to shells of lower potential energy, they release the same amount of energy that they absorbed to move out to the higher shell in the first place. So an electron gives off the same amount of energy when dropping from shell 3 to shell 2 as it absorbed to move from shell 2 to shell 3. The same thing happens for electrons moving between shells 1 and 2 and between shells 1 and 3. The energy lost is often given off as heat. In a later chapter, you'll learn how electrons boosted to higher potential energy states by sunlight are used to drive photosynthesis, a process essential to all life on Earth.
In this slide, I want to show you 3 things. The first thing that I want to show you is that an atom may have 1, 2, or 3 shells surrounding the nucleus. So look here, if you see hydrogen and helium, they only have 1 shell. The second thing in here, lithium and all these guys have 2 shells, while sodium and all these guys will have 3 shells. And this is very important because they will determine the chemical properties of the atoms. Yeah, so here are the shells. And another important property is that, if you remember, these guys, these chemicals will behave very different from this one, because this one will have their shells completely full. Well, this one, they don't have it full, so they will tend to interact with other atoms. So if you are not completely full like here, you will try to make chemical bonds with other ones. And we will talk about that in a second. So remember, the number of electrons in the outermost shell determine the chemical property of the atom. So now we know what is an electron shell. Electrons are placed in shells according to rules, and the first rule is that the first shell can only hold up to 2 electrons, while the second shell can hold up to 8 electrons. So let me show you an example to make it simpler to understand. So as I said before, let's put it in black. Let's see, the first electron shell can only hold 2 electrons. So here you can see hydrogen has only 1 electron shell, and here you have a space for 2 electrons. In here carbon, and here nitrogen and oxygen, they can hold up to 2 electrons. Now let me change to green, And if you see here in the second electron shell, in each of these cases, if you count the number of these guys, you have here, for example, 4 empty, 4 busy, and 4 empty spaces. So you have 8. You have 5, and you have 1, 2, 3 empty, 1, 2, and 3 empty. And here in oxygen, you have only 2 empty, 1 and 2. But in both cases, in all these cases, in these 3 cases, you know that they can only hold up to 8 electrons in the second shell. And I just want to remind you this octet rule that these atoms tend to gain or lose or share electron so as to have 8 electrons. Yeah. So for example, carbon, how many carbon would like to have? 1, 2, 3, and 4. So carbon is looking to gain 4 electrons. If you see here, nitrogen is looking to gain 3 electrons, and oxygen is only looking to gain 1 and 2 electrons.